so I'd just like to start off with a few acknowledgements, particularly that, so I'm presenting on the Wongal, the land of the Wongal people. So they're the traditional owners of the land which I am presenting today. And so I'd like to pay my respect to the traditional owners, both past, present, and into the future. I'd also like to acknowledge all of the students who've worked on these various projects. It's a lot of it is their work. So specifically Anshuka, Alex, Moa, Sylvie, Evie, they're all gold. I'd like to thank the people of Fiji who we've worked closely with on some of these projects, as well as the great APN team where some of this research, say, evolved out of. Vic Water and Water New South Wales and DPI for some of the data they provided us, and also Liz Symes specifically. And of course, Jason Brownlee for selling me lots of machine learning books and making me try to learn Python and machine learning, albeit a bit slowly. So as outlined by Travis, so I'm really going to start talking about drought and then end up in cyanobacteria. So the first thing I'm looking at is drought in the tropics, so specifically Fiji, and this was out of the back of some work we did in Fiji on a great project looking at all aspects of hydro and meteorological hazards, but also particularly how people, specifically in Fiji and Cambodia, they were the two sort of focus countries, how they adapt to climate, or are adapting to climate change, as well as looking at ways we can mitigate the impacts of climate, looking at I'd say it's more their adaptation to climate change, but also looking at, what are some of the in-country needs in terms of being able to be better prepared for these potentially increasing hazards, both, in intensity and sometimes in occurrence. So one of the focuses was droughts. The initial focus is really around floods, but we very quickly realised that in both countries, so one of the things that was very concerning to some of these, the people who we spoke to, and that perhaps they weren't they didn't have they didn't really have that much understanding of, was drought. So for example, in Cambodia, they're quite used to the, sorry about that. Oh, so they're quite used to the consistent floods that they get each year, which brings nutrition and water to their fields. But when we visited them, they'd just been through 2 back-to-back droughts. So, that's something that's, quite important that we sort of got out of the research. And so we decided to do a little bit more investigation into that. So a recent paper that came out about this looked at some of these historical and potential future drought impacts for the Pacific Islands. So that was one of the study sites. And so here you can see some of the droughts that have occurred recently. And in particular, they can have quite significant impacts on agriculture, both in terms of production, like in the case of Fiji for sugarcane, which is a major export, but it's also a really big problem in terms of their own nutrition. And so some of the key recommendations from that report was to particularly review the drought forecast standard operating procedures, but also to invest some time into developing and implementing early warning systems. And so that's what we'll sort of explore today. One of the key things, so I think what I'm going to try and get to with this talk is also, I mean, I'm not a a specialist modeler. A lot of my work is I'm getting my hands dirty in the field and that. I do use modeling as a tool, but I'd really love to work with a lot of you guys that are much more specialist modelers than I am, and data scientists and etc. So, but some of the work I do is, so I go out into the field and I'll actually interview. I've interviewed quite a lot of Fijian communities as part of this research, and to get an understanding of what they feel about what their issues are with the meteorological hazards, for example. And a lot of the people that we interviewed did indicate that they found that the early warning systems were unreliable, or they were provided too late, and sort of around that sort of thing. I mean, these are broader interviews, so there's quite a lot of information came from there. So these are just sort of nitpicking a few of the things. The other thing is, they definitely, identified, even though often floods and cyclones and that are the focus of their concerns, but, you saw that this sort of concept of drought was creeping in. And so they were particularly concerned about drought in terms of loss of income. They often, really struggled to produce enough fresh produce to feed their families. In that period, the price of fresh produce also increased significantly, and often they had to sell off livestock. They also were quite canny at actually picking up changes in the timing and intensity of drought. Now, I won't talk about that today, but we did do some correlations with those, what people observed and what was in the data. So here's an example of a participatory hazard mapping exercise. So, this is where we go in, we do ask questions about, drought, different hazards, and where villages actually sort of, so we have these maps that are geo-referenced, and they actually go in and put this information on the maps, and then we can digitize it, and we can use it in, in various ways. So, for example, one of them might be to verify, that there was a drought in the location that was impacting this area, and our models also said that. I mean, we don't get to that detail yet, but that's kind of the idea going forward. Now, with this research, so this is a lot of this is based on Anja's research. We just sort of started looking at it, and we decided to settle on using something called the effective drought index to represent the level of drought. So you can see these, the standard ones are the standardized precipitation index is the one that's usually used, but we also have another index that's called the effective drought index. And it's basically what it is. It's kind of calculated just from rainfall, daily rainfall, and it's like a weighted average going back in time of the rainfall. And because it's standardized, you can compare it between different regions, and it's actually quite easy to calculate. So that's what we decided on as a way of communicating information about, whether there's extremely dry coming up, severely dry, whether you're going to get, and you can also go the other side and look at whether it's going to be extremely wet conditions going into the future. So as I said, easy to calculate, only needs precipitation data. It's daily. We actually aggregated to monthly, but can be used at daily. It's good at identifying the start and end of droughts, for example. Because it's daily, it's not always useful when you're looking at aggregating up. But we just aggregated it up and it seemed to be fine. And it doesn't integrate temperature and other factors that might impact, the severity of drought. We're in the tropics, probably not a massive problem in this case. We also correlated the EDI with different vegetation indices just to see whether it was a good indication of the state of vegetation, particularly because, we're working in an agricultural society, or the villages where we were working. So, that made sense to do. And we found pretty good correlations with those vegetation classes. So basically, it's sort of a good indication if you're getting low production or high production. So the initial work, we developed a wavelet ANN, so artificial neural network model, to forecast EDI and EDI classes. And so we derived the EDI based on the CPC global rainfall data. We validated that data as best we could for Fiji with on-ground stations. And then we also investigated links between different sea surface temperature anomalies, also known as climate drivers, like Nino 3.4, which is the average temperature in the central region of the Pacific, and the Southern Oscillation Index, which is the difference in mean sea level pressure between Haiti and Darwin. So we used these to develop a pretty simple forecast, like 1 to 2 months ahead. And I mean, this is an example of one where we're looking at the classes. I mean, one of the key problems, of course, is that the classes, in Fiji, most of the conditions were normal. And then, we only have a limited data set, like back to 1980. So we only had a few off-normal situations, and we probably predicted about the same amount right as we did wrong. So not particularly good, and we didn't really seem to pick up on the be able to predict the drier periods, those three specific ones that I referred to before. So a couple of things to do going forward, is potentially look at reclassifying it, getting a better understanding, and, basically assimilating data from the interviews we did, trying to maybe, better understand whether we can reclassify these situations to be more relevant towards Fiji. Anyway, so the next thing we did was to go down, try and do a bit more. So that was basically, we just did a forecast for specific stations that we had data for, as well as, that's where we focused on, but they were from data from the CPC data set. In this case, we tried to actually do a bit more of a spatial space-time forecast. First way to do that is to do the traditional canonical correlation analysis. We did reasonably well. Again, predicting a month ahead. So, we're going to get extremely dry conditions next month, or the EDI is going to be, this value in between. You can also provide confidence intervals, etc. Then we tried to step it up a bit, and this is where, I had to, really step up my learning, and probably where you guys are going to go, oh my God, what is he doing? But anyway, we started to look more into using LSTMs, which makes sense for time series data, working in CoLab, assimilating data through Google Earth Engine, and to slowly start developing a more operational tool. We're still going. Here's an example of one of the model setups. Like, you guys are, much more familiar with the table on the left, but we did play around with the different parameters just to try and get it better. And so, what we can do is we can get these forecasts. Now, you notice this sort of weird, sort of laggy look in the graphs on the right, and I'll explain that in a bit. What you're seeing there, and here's some of the spatial forecasts that we produced using that. So you've got your observed, then your predicted, then you've got your residuals, so how far off you were. And we've got different models. So we've got a univariate model where we just basically used EDI to predict EDI at each location. Then we've got a multivariate model where you predict EDI at single location using data from the whole area, and then you bring in sea surface temperature. And so obviously the two multivariate models are doing better. And again, we're predicting 1 month ahead. So we do okay. I mean, there's a lot of limitations in this, my skills and time to get the skills. We've got a fairly short data set, 1980. Is it enough? of course, I haven't quantified uncertainties here, which is something that we'd have to do going forward, and that's something where I could definitely work with you guys to better do that. And one of the things, like, we're not really forecasting much better than, for example, taking the average of 3 months EDI to predict the 4th month EDI. I mean, that's basically what we're doing also with our model, is we're going through training the data on 70% of the data set, but we're doing predictions of the next month based on the 3 previous months' data, so both EDI as well as SST. It is a bit better, but not too much better. And it really doesn't matter how fancy these models are. I mean, I can get, pretty similar results just using standard regression, or, what I'm very familiar with which is generalized additive models. So, we need to start thinking, what other data can we assimilate into these models to get there. So moving on, I mean, this is just a few ideas. I mean, one of the things is, I repeated the thing. So, as I was saying before, really try and explore the links between drought and other anomalies that might be linked to climate patterns, such as things like geopotential height fields, the ocean thermocline depth, and really also play a little bit more with the lag between when these fields and then when they impact drought over land. And when I first started out, I wanted to really try and sort of get a bit better idea how whether we could using machine learning with its foundations in image and pattern recognition. I mean, one of the things I was really interested to know is, I mean, basically you've got patterns happening in the ocean and you've got patterns happening in the over land. So, these sort of different circulation patterns, and you've got, drought, in different regions. Even though Fiji's small, I mean, you still do get some differences. And I was wondering, what's a good way to see if, you can find links between when a pattern here and certain patterns here. And we're kind of doing that, but I don't have enough understanding myself of really know whether we can get that far. So I mean, if I can understand the names of the models, I mean, I'm thinking about something like a lagged correlated double convolution LSTM model. So I don't know if they exist, but maybe you guys can understand where I'm getting to. So then this work sort of switches over to another problem, and that's really around predicting blue-green algal blooms. And so I've started off with a student example. So this is from Evie, and she's doing one of our ENVX 4001 GIS remote sensing and land management students, and she did a project on Bonnie Doon. So I'm not sure if you all know, but Bonnie Doon is very famous from being in the movie The Castle, which is a very well-known Aussie iconic movie. So how's the serenity in Bonnie Doon? Now, the water quality looks pretty good at the moment, but it does get pretty bad. So now, Bonnie Doon's, of course, down in Victoria. So, and we're interested in Lake Eildon. So yeah, it does get pretty bad. So, I was going to say, you can actually rent the house that was on the film via Airbnb. So if you want to experience the serenity from the castle, you can actually go down and stay in the actual house they filmed it in. Now, Lake Eildon does have its problems, and if you look at this image here, you probably wouldn't want to be swimming in that water. And indeed, you can see even in January of last year that they had issued warnings to urge tourists not to swim at a popular holiday spot. So you can imagine that was a bit of an issue. Of course, if you do swim in it, it can make you pretty crook or give you skin rashes, all sorts of weird stuff. Not particularly good. And there are potentially long-term health impacts as well, which are being investigated, such as links with motor neurone disease. Now, before I move on, so one of the things is it's quite a lot of interest in seeing if we can better predict, when these blooms are going to arise. But it's not easy to, sort of go, sample, for example. Water New South Wales does do regular monitoring, and of course, when there's a bloom detected, then they'll go in and do event monitoring or sampling to try and, get a better handle of, where it is when. And they work on an alert system, so they've got the green when it's okay, amber's kind of on the way there, and red is, when you have to start putting up signs saying don't swim here, and all that sort of stuff. So, there's quite expansive waterways throughout Australia, very hard to monitor them all. So part of what I've been looking at is, what sort of data sets and can we use to try and, help monitor for these blooms. So, because I've got so much teaching on, luckily I've got these students, and so we can run some of these projects through these students. And so here's an example. So what we've done is we've taken data from Landsat and Sentinel, and in particular we've taken some of the bands from these satellites, and as you've seen in the previous picture, it makes sense that I can see that this water is kind of a bluey green colour. So cyanobacteria emits, has two pigments in it, or they do have more as well, but two main pigments. So there's the chlorophyll, which is the green colour, and then they've got another one called phycocyanin, which is a more bluey cyan colour. And so they're quite characteristic to cyanobacteria. So it makes sense that if you have satellite imagery that you might be able to pick up these blooms, particularly in the bigger waterways when they're significant enough. So we went in, had a look at, predicting the biovolume. So this is just purely predicting, it's not forecasting, predicting biovolume. And we did find quite good correlations, for example, with the different bands in the Landsat imagery. It seems to be not as good as Sentinel, but I'm not sure I believe these numbers entirely, as a later student found quite good correlations, particularly with the blue band in Sentinel. So Sentinel's, of course, got finer resolution, particularly in band 2, 3, 4, and 5 compared to Landsat. So, and these are all Landsat 8 and Sentinel 2. And so we did some modelling using random forests, and so the training data set in bag, out bag RMSE around 0.45. Not too bad. Correlations quite good. So that's not a bad. That's not too bad of a correlation. So that's between biovolume, and so biovolume represents about how many organisms there are in the waterway versus how versus so what's been. Yeah, well, basically biovolume is a representation of how many organisms there are in the water. In the old scale, they used to talk about how many organisms per mil is the old measurements, but they now do biovolume. So this is an extension of that, and in this case, in the previous case, so we're looking at a whole lake system, as well as, I mean, you know, we were looking at a lake system. We were particularly correlating it with a site close to Bonnie Doon where they do the monitoring, but you know, you could sort of extend that across the whole lake system. In this case, we're actually looking at a river system. So this is actually the confluence of the Murray. So the Murray goes off down that way, and the Darling River goes up that way. And so we've got a number of sites, mostly at weirs. I think, I can't remember the weir numbers, but I think 10's probably just downstream of these. And it's basically the same concept, but the difference is that the conditions are quite different. So you've got a large lake, and probably the water is a bit clearer. In this case, you've got a river system. You've got, you know, faster flowing water, particularly coming down the Darling River. So from the north, it's probably more turbid. The Murray's a little bit cleaner, depending on what time of year and whether it's after rainfall, but so quite different conditions, and plus, you know, not a large area. So yeah, so it's quite a small area. Now, the other thing about this project, and this is what Liz Symes brought in, was we also added in, and as I was saying in the previous effort with the, you know, forecasting of droughts, is we also introduced dust data, and the idea behind that is that dust carries nutrients. It can also carry spores as well, and things like that. So, you know, if you do get dust coming through, settling in the water, the idea is that that can introduce nutrients, and therefore, you know, can facilitate algal blooms. Generally, algal blooms are phosphorus limited in Australia, so any introduction of, for example, phosphorus into the waterway, which, you know, would happen in the case of dust, might facilitate algal blooms. So yeah, so we've got the satellite data, which we know can reasonably track algae in larger waterways. We're looking at river systems. We're also looking at whether dust, you know, high volumes of dust coming into the system might also influence algal blooms. And then, you know, of course, just looking at the water itself. The other thing we did do as well is of course, introduce typical climate variables that we measure, because we know, for example, that temperature drives algal blooms. So algal blooms like it when it's warm. And we know that sort of above 20, 22, up to 24 degrees, when you're starting to climb above that, then conditions start to be quite favourable. So it also made sense to include in the model different climate variables, which are easily picked up from the Bureau of Meteorology, or SILO. So here's an example. Here's the coordinates of the different sites that we looked at. So here we're looking at specific sites. These are the different variables that we ingested into the model. So you can see these are things, these are the data that we got from SILO. And these are the different dust data that we collected. So that was through DPI, the dust track data. And the other thing is that we also have water quality parameters themselves. So we do have things like nutrient concentration at certain sites. We didn't use this because it's not something that's regularly collected and is as in on a, say a weekly or so basis, maybe monthly. But we wanted to sort of pick this model up to more like real-time forecasting. And I've in fact also run the model just on climate data as well, but I won't go into that here. So and this is just in this example, the student. So this is work done by Moa. So she's a Dale student, like she's one of in the talented student program. So if there are academics at Sydney Uni here, I definitely recommend putting in projects through that program. I think in all, I've been really impressed with the quality of students. Now, you have to have a very good contained project that they can really sink their teeth into. But, you just set them to work and they're passionate about it, they love it, and they learn really quickly. So this is an example of one of the models. So this is a generalized additive model. Something is more what I understand. So that, again, it's just a prediction. And so there were 4 variables that seemed to be, correlated with biovolume data. In particular, as you can see, as temperature increases, so does the log biovolume. As the rainfall increases, so this is a rolling average rainfall going into the past, that you can see as that increases, then you also see, so that's probably that runoff that can trigger events. And you can see the inverse relationship between in this case, we focus really on the sentinel blue band. And so as that value increases, the relation, it's an inverse relationship. And again, as dusk increases, you see an increase in the log biovolume, which I think all of these things I would expect. And the model's not brilliant. It's it's not brilliant, but we can we can provide some sort of estimate, of what that what that biovolume is. And of course, we could also, run these as a more of a classification problem, for example, where we predict whether the location is in green alert level, amber, or red. And so, that's possible as well. And we can also do, we can do spatial validation, for example, where we leave a station out. And then we see, if we can predict that sort of station. So these are all things, sorry about that. Here he goes. So that's one of the things that that we can do. So so basically in the right, and the other thing is in the right conditions, when we've got all the right conditions, we can probably advise almost real time, which places you might avoid to go swimming. So if you think about the Bonnie Doon example, and again, in the right conditions, we can probably advise authorities, where to sample or where there might be an issue. And we can definitely get a better understanding of the spatial and temporal distribution of algal dynamics. Okay, and that's a bulk algal dynamic. It's all algae together. We're not talking about specific species. There are heaps of limitations again with this. Things like, Sentinel passes every 5 days or so, Landsat 8 about every 16 days. One of the things that, I've suggested is that, if you do have a regular sampling program, I mean, maybe you can look at adjusting it to basically align with satellite passes, because that will at least allow you to build more data to better test the usefulness of this satellite data. Of course, satellite data is not always continuous, so you do get breaks in the data and that sort of stuff. The other thing is that you've got to make sure that all your physical samples and your satellite passes and for specific regions all line up, and so you can get huge data loss. I mean, you might have 35,000 data points from Water New South Wales, but in the end only 300 are suitable for developing your model on. Other interesting things are like the actual time of day that the satellite passes. I can't remember. I think that this location or the last location, so the confluence of the Darling and the Murray, I think it's around about 9 or 10 in the morning, which is probably not too bad. But for example, later in the day, as it heats up and as the light intensifies, some cyanobacteria can actually control their buoyancy, so they actually move down in the water column. And so you've got to think about all of this stuff when you think about, is my model okay? Of course, massive limitations on my time and skills, and hopefully out of today, something moving forward, we might be able to work on some of this. Like I've said, going forward, New South Wales Water, for example, could think about whether it is possible to better align their regular or routine monitoring with satellite passes, and whether that can be useful and manageable. I mean, it's pretty hard to do it all on one day, but at least on the same day, getting out there should give you a reasonable matchup. And there are a lot of other data sources out there that I haven't explored, which are evolving quickly. I can think of the planet satellites, the little CubeSats. So they've got things like SkySat and the Flock, which pass over regularly. I mean, Flock I think does RGB. SkySat I think actually does the multispectral stuff. So, and you're talking about sub 2 meter resolutions. And also that that much more regular passes, so it could be super useful. That's where you also can start. The other thing, of course, is with cyanobacteria is that not all cyanobacteria are toxic. Other things in the water can actually make it look green, such as just algae. And so, you can start maybe separating out, potentially what are toxic cyanobacterial blooms versus non-toxic. I mean, that's pushing it a bit far, but certainly in situ measurements using hyperspectral imagery are looking at getting to that sort of level of detail. So there are possibilities. And so that's using things like, the multi-sensor platforms that you can actually deploy in the field. As part of this, and particularly also I want to acknowledge Sydney Informatics Hub, who did a lot of work on preparing a lot of this data that was sucked out of Water New South Wales database. It comes out, it's not easy, it's not really in a form that's very useful for modelling. So, there's a lot of wrangling, lining up of data, trying to build these data sets. So we actually did produce a new database that, potentially could work in a map format like this. Going forward, like you could even, I mean, this is what the existing tool is. It tells you what the most recent measurements are. This could have an additional tool that gives, for example, what the outlooks are for algal blooms going forward. So you can plan your holidays better, for example, to Bonnie Doon. So I'm going to wrap it up here. Because I think I also didn't mention I'm actually still battling with COVID. So because I've got 2 teenagers, so it was only a matter of time that I got it. So I'm going to wrap up and have a bit of time for discussion. But I've got heaps of these kind of projects that really need data skills, and probably more advanced data skills than I've got. Things like I've got a project predicting E. coli in irrigation source water. It runs parallel to the BGA projects. It's really about, when irrigators irrigate their crops, particularly in horticulture, if there's more E. coli than a certain number, that has implications for when they can harvest and send the produce off to market. So one of the things is developing a tool that can actually predict when these situations are in fact the case. I mean, it's hard to do because it's very hard for a farmer to take samples and send them off to the lab. It's expensive. It takes a day or two before he gets results back. By then it's too late. So it's trying to get this data more real time. Text mining, heaps, fisheries interviews, Cambodia focus groups, all the surveys we do, analysing that survey data. Things like detecting plant disease using multi and hyperspectral imagery. I've got projects starting in more in the high-tech urban ag space. Making these things self-running and that kind of stuff. The other thing going at the moment is also, like, for example, monitoring streamflow networks using camera traps, which is something that I've been working on a bit with Aaron and Glenda. So, these are all things that I love working on, but I think there's plenty of room to get some more data skills on board. So that's pretty much it for the talk for now. So hopefully it was interesting, and I'll try and answer any questions. I'm not sure if I'll be able to, but we'll do our best. So I'll leave it at that.